Take it away, guys.
Okay, thank you. Okay, so hello to everyone. We are Cram, and this is our automated large volume micropipette of 500 microliters to 5,000 microliters. As you can see in the picture, this is us from left to right. Is Luis, then is Mateo, then is Nathan, then is myself, Alejandro, then we got Corinne and Christopher, sorry. This is the people that conform Cram. Okay, so today my teammates and I will give a device overview where we explain why the purpose of the design device, what are its main parts, and a brief description of its functioning. We will also provide a list of the given customer needs and how this were met in the design process. We will then show the evolution of our design, beginning with what was provided as a guide up to the finished and full functioning of the design. This explanation will demonstrate why changes were made and will show the physical changes that were performed. The functioning of each of the separate parts will then be explained individually, as well as how they work together as a system for the micropipette to work as a design for. And finally, the mechanical analysis that was performed will be explained to demonstrate that the micropipette will not malfunction under the correct circumstances. These are 3 renders of our final design. In the first picture, you can see an isometric view of the full system, as well as in the second render. And in the third render, there's an extruded cut showing the internal parts of the design. And next slide. So these are all the internal parts. Each of them will be furtherly explained by my teammates. But as you can see on this exploded view, the design consists of an EMA 17 motor, the outer housing, the tool plate which was provided to us, a collar and a lead screw nut, the outer pipe, the limit switch, the receiver tube has a O-ring gland, the bottom housing plate, and the tube remover. All of these parts will together function to make our device work properly. They will also be explained furtherly.
Okay, so our team developed the design of our large volume micropipette to fulfill an extensive list of customer needs. And for this presentation, we designated the customer needs that we deemed most critical to demonstrate with stars here on the left-hand side of the table. The customer needs for our micropipette can be divided into a few different categories, the first of which here is fluid dispensing. Our pipette design needed to be capable of depositing a maximum liquid fluid volume of 5,000 microliters and a minimum fluid volume of 500 microliters. It also needed to operate at a maximum rate of 2,500 microliters per second and a minimum rate of 200 microliters per second. Another aspect of the customer needs was safety, which in essence meant preventing any sort of cross-contamination during the operation of the pipette. We needed to implement a mechanism that would eject the disposable pipette tip into a waste bin within the bioreactor enclosure, as well as incorporate a fail-safe function to prevent the prime movers from exceeding their range of motion. The next category of needs is external interaction, which has to do with how our micropipette device interfaces with the other components of the bioreactor enclosure. It was especially important to ensure that the pipette housing would integrate with the no-plumb stool changer. And finally, our pipette needed to satisfy several physical design constraints. In addition to establishing an operational lifetime of at least 10 years, the total bill of materials cost needed to not exceed $100, and it had to fit within a specified volumetric envelope. It had to weigh less than 5 kilograms with its manual assembly time kept under 5 minutes. And it was also required to use an EMA 17 motor for the main pipette drive.
Starting with the design process, sorry about that, my mute button's failing. We designed most of it to use 3D printing rapid process. This way we had a very high turnaround time for making design changes. We focused on PETG for its design stability and because it ease of access, as it was very readily available to us. We used the Prusa 3D printer located on the right, and we use STL models to convert the 3D models developed on SolidWorks into path path tooling that makes it easy to print. So our initial design started with a basic one that was given to us early on. Quickly, we realized that it used a lot of material unnecessarily, as well as created a couple of problems. So we scrapped it and started from scratch. Our first look at it was our housing for the design parameter of dimension. And early on, we thought that we would enclose the motor itself to make it look more appealing, but we realized quickly that it was a waste of material, as well as increase the time it took to 3D print it quite substantially, adding about 10 hours, which just wasn't needed. So then we moved on to the shortened housing design that you can see in the first or in the second square, before moving on to the third one, which incorporated Knoll's tool exchanging kit. We finally wanted to make it aesthetically pleasing, as well as further limit the amount of material that we used, which also limits the amount of time that it takes to actually build on the 3D printer, which led us to create those triangular holes in the side. This also allowed us to put tools inside of it, so we could do diagnostic work if something was failing, as well as do fine tuning if necessary, which luckily we didn't find necessary. Once we did that, we went to the outer pipe. This controls the fluid volume that we can accurately measure, as well as how much it's going to be ejected at what rate, keeping the rate of the motor constant. Basically, we change the cross-sectional area of the interior of the outer pipe. By changing that, we can change the fluid volume, because as you increase the area, you increase the volume that's getting sucked up, as well as the depth. First, we did an initial groove design for one collar at the very top. This was so we could connect to the NEMA 17 motor using a collar that you'll see later on in the presentation. And then we also connected a second groove on the bottom, so then we could connect the pipette tip ejector. This was later changed because we found it was unnecessary to make a second groove. We could just build the second groove in, and that's what you see on the far right. We also added a parallel plane that cuts down the side of that groove. This interfaces with the wall of the pipette itself, or the pipette housing itself. This allows it so no rotation is occurring when the NEMA 17 motor is moving, and just sets another constraint. The tip remover changed quite substantially, but mostly it didn't change the overall look of it, it changed height. So early on, we figured that we would use an annual region to eject the tip. And the way that we would do this is that the lower collar would interfere with the upper portion of the tip remover, and this would, by extension, push down and eject the tip. Our first design ran into the issue that it was interfering with the screws that connected the lower receiver tube to the housing itself. So we had to change it from a circle to the semi-circular shape that you see in the middle. This eventually changed because we realized another way of adding the tip receiver tube to the housing, changing the tip remover. This led us to make a more robust model, as well as making it fully circular. We also added fillets, so then there was no stress concentration. But of course, we still did FEA analysis to make sure that wasn't an issue later on. The receiver tube changed in some ways, but for the most part, it stayed the same, only changing it in terms of adding a collar. So then we could add an O-ring gland to it. And we decided to put the O-ring here on this system, because this way we could change how much. So long story short, the area of, that this has doesn't affect the volume that's being absorbed into it. So we can make the wall of the O-ring as thick as we want. So then we can make it so it's safer. And it just made a lot less issues. We also included the fan slides to increase the mounting hole interference. So then we would have pure mounting on the housing itself.
So now we're going to talk a little bit about the device functions. As you can see here, we fulfill customer need number 5, where it's able to fit inside of the envelope of an appropriate size, with dimensions of 86 by 58 by 170.4 millimeters. Now, as you can see on the right side, this is the main functioning of this pipetter, where it's very simple and reliable. And there's a lead screw coming from the NEMA 17 motor, and a lead screw nut is also attached to it, as well as a collar. And those are both attached to the outer pipe of this assembly. And an Arduino program is used to be able to dictate which steps one needs to take for the appropriate amount of fluid volume that one is trying to what one is trying to get. And so this satisfies customer need number 28. Now, as far as interfacing, this design needs to be able to interface with several components of the enclosure, including the Vista Rack tips, as well as the Noel Thomas tool exchanger. And for this design, it was required to be able to create these indents into our housing to be able to fit the appropriate connections, such as what's highlighted in this red circle here, the magnet, as well as different electrical components that can be used to attach to the XYZ system itself. And we also incorporated different fasteners to be able to assemble this a little bit quicker. And so this overall is to satisfy customer need number 21. Now, as far as the tip disposal, as Nathan mentioned prior, we went through many iterations and we finally found a tip remover that we were comfortable using. And so this is what is being used and is in play on the pictures to the left for when the tip eventually needs to be removed. And then in order to put the tip back in, it would have to be manually put in. And so then then everything kind of falls back into place again. And this satisfies customer need number 19. Now, as far as the fail-safe function, we incorporated a limiting switch when the pipette tip is eventually fully removed, as mentioned in the previous slide, in order to avoid collision and damage of the other parts of the system. And so this satisfies customer need number 22, which incorporates a fail-safe, preventing the prime movers from exceeding that range. Now, as far as the calibration of our design, we went through multiple steps. Of course, we began by zeroing whatever we were using to hold the liquid volume, and then we went ahead and adjusted the Arduino code shown on the bottom left. And what we found was, in order to properly dispense all of the liquid, we needed to create a small air cushion, as highlighted in the code. And so we were able to take in that small amount of air, then take in the fluid volume that we needed, and then dispense all of it like that, so that every drop was able to properly dispense, properly eject. And so then this was then measured in the lab's fluid, or the lab's measuring apparatus. And then the process was repeated for multiple volumes, or for multiple masses that we were then able to calculate from the measurement. And we were then able to develop a calibration, a piecewise linear curve fit. And this was then able to satisfy need 17, where it's able to deposit the minimum and maximum fluid volumes. As you can tell, there are three different ranges highlighted by the red, blue, and the green linear fits for our experimental data. And we were then able to go ahead and understand the resolution volume per step in order to assess whether or not the fluid volume that we were able to eject was within the proper tolerance of plus or minus 10 microliters. And as you can tell, our design is able to meet that requirement.
So another customer need we needed to satisfy was the restrictions on the fluid flow rate, which is shown in the bottom right corner. Since we are using a stepper motor, we can easily control the rate of rotation omega of this stepper motor by pausing between steps or sets of steps. And so using a simple fluid flow analysis, we were able to determine based on our geometry that omega needed to be between 8.5 and 106 RPM to satisfy these restraints, which is perfectly achievable with this motor and the relevant code. So a crucial part of the design process was ensuring we had an operational lifetime of more than 10 years. And so as we designed our device, we designated two critical parts, the tip remover and the upper collar, as parts with relatively high bending moments and forces, as well as significant cyclical stresses during the operation of the device. For the tip remover, we did a static and dynamic analysis based on the simplified model shown in the diagrams in the middle of the page here. So we identified the location of the maximum stress, denoted with the red dashed line there on the left diagram, and we were able to prove that this stress was below the yield stress of the material, which was PET-G for this part. So this part would not fail statically. Then using the theory of fluctuating cyclical stresses, we were able to find and show that the equivalent completely reverse stress lies below the endurance limit of the material. So we are able to assume it has an infinite life. Similarly, we determined again the location of maximum stress in the upper collar, and that's again shown by the red dashed lines in those center diagrams, and performed a static and dynamic analysis. We showed the maximum static stress experienced was below that of aluminum, which is the material of this part, and then dynamically with conservative estimates for the Marin factors, we could show that the completely reversed stress lies below the endurance limit, and again say it has infinite life. So we can conclude that our operational lifetime of all manufactured parts is well over 10 years.
A simple mass analysis was completed to ensure we met the customer need of being less than 5 kilograms of mass. As you can see here, we're well below that limit, coming in at 554 grams. Our assembly time was predicted to be 4 minutes and 34 seconds using the Boothroyd and Dewhurst assembly time estimation technique, which estimates handling and insertion time for each component. On the left is an example of this for the outer pipe subsystem. We also physically assembled the product and timed it to determine our experimental assembly time of 4 minutes and 4 seconds. Both of these are less than the customer need of 5 minutes. And lastly, our bill of materials, the OTS cost for our full assembly totals to $85.68, which is below the budget of $100. These are the sources referenced in our presentation today. Our group would like to thank you all for attending our presentation, and we would like to open it up for questions.
All right. So Dr. Nemi had to step out to handle an emergency. So he asked me to take over. And we've got about 10 minutes left. So if there are questions from the panel, now is the time to ask.
I just want to say a good job, guys, on the hand calculations and showing your design evolution. I liked your diagrams showing the cross sections. That was really helpful to see where you thought the failure locations would be. I was wondering for the tip remover, how would you manufacture that one?
So that's 3D printed. We actually found that it was really fast 3D printing. It took about 10 minutes to actually 3D print the tip remover, and it's quite robust. It's this plastic part right here that you'll see. And it just, when you physically have it in your hand, it has very little give. But honestly, I think we're just 3D printing, keep it consistent with 3D printing. Of course, we could also injection mold it and use that method. So if you wanted to mass produce it, just injection mold, but keeping it plastic and or a polymer, staying away from metals, I think that would be the good way to do it. Just because it's not necessary to have that high of a physical strength. And plus it would cost more to make it metal. Does that answer your question?
Even if I don't know the dimensions of this, but is the 3D printer accurate enough to get those radiuses that you I guess you want around? Okay,
yeah,
I can't really tell.
Yeah, we actually gave it. So I have the model in my hand. It keeps itself constrained because we made the collar on the receiver tube a little bit bigger than was absolutely necessary. It gives it a little bit of boundary of error, which 3D printer is able to meet every time. I've printed about 10 of these actually at various heights when I was trying to fully calibrate it. And I never had an issue where it was out of alignment, which I think that's what you're mostly getting at, is getting out of alignment and being too big or either too small to accurately fit within the housing unit where it interferes.
Thanks.
Yes, this is Tom Singer from Northrop Grumman. You were showing your tool adapter, the triangular shaped deal, and that's got some electrical connections on it. And I guess I'm curious, where do those connect? Do those go through your pipetter, or I mean, where are the cables running, and where do they come out?
So the cables themselves, if you see where these holes are right here, it runs up the side of the housing unit until it connects right to the top of the motor. Right now, this is just a preliminary prototype. The limit switch is also right here, which you can't really see, but the wire also runs up along the same side. Well, it doesn't run that far because it's just going to here. In the future, what I want to do is I want to change the housing to a certain degree to add like a trough or a channel where we can have the wires directly go up the side of it, either the corner, up the middle. This will keep the wires out of the way. Right now, they aren't in the way, but they are kind of an eyesore in that you can see them clearly through the side if you were in person. But mostly they just run up the side of the housing. I'm not sure if that answers your question.
Yeah, I was just curious to make sure that you had some accommodation for there. Something I appreciate that you and a lot of the other groups are looking at calibration curves, and I'm wondering what happens as your system ages and as it's used over its 10-year lifetime. Do you expect the calibration to be affected, and is there some capability or requirement, I guess, for a user to repeat the calibration from time to time?
That's a really good question. And so it's kind of a two-part answer. So if you look at the graph on the left, you'll see that we did a piecewise. And the reason we had to do a piecewise is because we lubricated the O-ring, and the lubrication of the O-ring, we couldn't get the specified amount. So when we are doing the max volume, we get more accurate than when we do the smaller volume, because we have the O-ring lubrication getting within to the receiver tube and the outer pipe. But without it, as you can kind of see on this curve, it's perfectly linear. And the reason it's like that is because we made the outer piping a perfect circle at a set radius, which was 7.5 millimeters. And with that 7.5 millimeters, it stays absolutely constant. So unless the aluminum itself degrades over time, which it shouldn't within the 10 years, because it should only be interfering with air or whatever air-like substance is in the design itself when it's put into the incubator. So it shouldn't degrade, but it is a pretty easy calibration to do as long as you had an accurate measuring unit that we had. But I don't think it should be an issue within the 10 years that it's allotted to function.
Okay, I'm thinking maybe potentially more in the drive components And I would certainly expect that, once you get out to a reasonably large number of steps and a large enough volume, that it'll still be fairly linear. But with like backlash in the system that grows over time, you may the intercept may be changing a little bit there.
That's a really good point.
But if you're talking on the order of 500 microliters, maybe that's not as big a concern as for some of the groups that are focusing on smaller volumes.
Mm-hmm. What I was really happy about ours was that we were able to get, for the most part, besides the really very small volumes, we were able to get within 5 microliters. We actually showed the outliers when we were doing it to show what is our extreme limit of accuracy. But when you say the backlash definitely would be an issue. And one of the things that we did have problems with was backlash. And change the design again, I'd probably change the lead nut that we have on the shaft to get an anti-backlash nut. But like you were saying, I don't think because we're doing the large volumes, that would be an issue. But if we could make this one also do the medium volumes, which is a limit of 100 microliters to 500 microliters, then backlash, would be a problem, especially 10 years down the line or 15, or if they're going outside of the life range of our particular unit, that could lead to an issue for those small volumes. But for the 500 to 5,000, I don't think it'd be a problem. No, that was kind of a drawn out answer. I'm not sure.
Okay. We might have time for about one more question, although I think the next group has popped in here, but maybe one more quick question since we started a little late.
So I guess I'll be the one more question. When you were talking about ejecting the tip is being ejected, but then you said it would have to be manually put in. Is that a lab researcher is going to have to reach into the machine and attach a new pipette, or did I miss something there?
So the tip ejection is automatic. When Mateo was talking about manual, what he means is from our understanding of our criteria was that the pipette system itself would move to a location where the pipette tips are housed, and they would be housed linearly, and the whole apparatus would go down and interfere with that next pipette tip and then go on its way. So I don't think we need a human interference. We would need an apparatus, which we assumed was going to be part of the housing team requirement, that would allow us to lower this apparatus into the next pipette tip and then do whatever it's
so not manual, but not a part of your system.
Yes.
What would your alignment tolerance have to be for that system in order to successfully engage a pipette?
1.5 millimeters. If I had it.
Is that feasible?
Done.
Is that something that you guys have talked about at the interface of the systems?
So I have talked to the XYZ team, which is the movement team, and from when I talked to them, they said that they were able to get it fairly accurate, though they did not give me an exact limit of their accuracy when it comes to movement. But they said that in theory,
you better pin them down on that.
Yeah. Oh yeah, definitely. But they said in theory they should be able to get it once calibrated, because they were saying that they were still working on their calibration at the time that I was speaking to them, that they should be able to get it within some bounds within our curvature. So to make it a little bit more, I guess, feasible, to give us more error, what we could do is we could add a bigger fillet, this end right here. Right now we have a very small one, but we actually have about 2 millimeters to work with. So if we made this fillet more needle-like, we could expand those bounds, so we don't have to have that accuracy of 2 millimeters that I'm thinking that we're going to need right now. And I think that would be the most optimal way of solving it. And honestly, it would limit the amount of weight too, because it would reduce the weight of, though very small.
Oh, you're not worried about that. But yeah, definitely the required positioning tolerance, which is going to play into, you know, your XYZ system and also your whatever is holding those pipettes in place and how much kind of wiggle room that gives the tip.
Which they would need that tolerance to be able to get the pipette itself over whatever test tube that they're using too. So I think it's a double edge. If they're able to get it over the test tube, they should be able to align the pipette with the receiver.
Maybe.
All right. So let's wrap it there, since we're a little bit over time, and the next group I think has popped in. So I want to thank you guys for sharing your design with us and all of your hard work this semester to take the initial prototype to what's hopefully at least the basis of a future commercial product for the UF Biofoundry. Let me stop the recording so that we can do the transition. Oh, and Dr. Nimi's back. Okay, so stop recording.